Okay, folks, the video is on. So, we left off talking about meth, which is always an interesting topic. So, so we were talking about methamphetamine and how one enantiomer probably will wreck your life, and how the other enantiomer will just let you breathe a little bit better. And so I showed you guys that, and then you can see the molecules at the top, and one has the wedge indicating that the methyl is coming out at you, and that one right there shows that it's aimed backwards. But it's not super easy to see with those two pictures that they're mirror images, so that was on the next slide. And you'll also notice that there's a D and an L in the front of those two words, and we will get to D's and L's and pluses and minuses in just a little bit. Also, you'll notice another thing that we have looked at before, S and R, so we did those things also. Any questions on this, folks? Yes?
Is it possible to take a Vicks inhaler and turn it into methamphetamine?
That would take a whole lot of work. You'd have to break some bonds and make some bonds, and I don't know that it would be worth your time. And I wouldn't advise that from a legal standpoint either. Alright, so this was a slide where it positions them so that they look like mirror images there, okay? So on the left, we have the S version, which is also the D, and on the right we have the R version, which is also the L. And again, I'll get to L and D in just a second, okay? So are we okay, folks, with the chiral carbon, how it's pointed out right there, that this carbon on both of the molecules is bonded to 4 different groups? Are we okay with that? So we have a methyl and we have a hydrogen, and that's pretty obvious that those two things are different, right? And then over here, you just have to imagine that it's a big blob and ask yourself, is this blob different from this blob and this blob? And is this blob different over here? And are all 4 of those things different? Yes, they are. Okay, so you have a chiral carbon right there. So questions on this, folks? Okay, so if you go and you take a look at one of those little Vicks inhalers, you might notice that it's not spelled methamphetamine. They change the spelling a little bit to throw people off so they don't think it's methamphetamine, but they only change it so much it'll be like methamphetamine or methamphetamine, or they'll take like one letter out, and it's like, why did you even bother? Why didn't you just call it something else? I don't know. But anyways, so go to CVS, check it out. Yes?
So the reason why that's the chiral carbon, it's because it's bonded to 4 different R groups. So, because from my understanding of the videos I watched, because I missed the last lecture, like why wouldn't the chiral carbon be on like the carbon that's on the benzene right there, that where it branches off?
Are you talking about that one right there?
The one more left.
This one right here?
Yeah, why wouldn't that be the chiral carbon?
Can anyone else answer him, just from what you've learned?
Because double bonds, they count as 2.
Yes, because this one is double bonded to this one right
my
here.
bad. Yeah.
So yeah, we consider that as it's bonded
So
to
it's
the
only
same
3
twice.
R groups, right?
Yes,
Okay.
yes. So it would be like if you were bonded to 2 hydrogens.
Mhm.
It's the same thing. So let me take that off right there. Oops. Okay, so we have the 3 different groups that our black carbon right there that's labeled chiral carbon is bonded to. So if I circle them with the different colors, can we all see it better? Okay, so yeah, that's where they're at. Any other questions? That was a good one. No?
So,
Yeah, go ahead.
looking at this, even though they look almost identical, the difference is, of course, they have different effects based on the elements.
Absolutely, absolutely. So they're gonna interact with our cellular receptors differently, or not at all, or stronger, just depending on it's really interesting how our cellular and our enzyme receptors are so specific with how they interact with different molecules. Like, these are obviously like beyond similar, but you know, one gets you high and the other one just clears your nose, right? It's way different. So the D and L thing, I'm gonna hit on it a little bit here, explain a little bit, and then again we'll come back to D and L. So the Dnl designations are used in sugar chemistry and in amino acids quite a bit. And what you'll see is most of our naturally occurring sugars are D, and a lot of the naturally occurring amino acids that appear in our proteins are L. So these two things are mirror images of each other, just like when we had R and S that were mirror images of each other, but there's a little bit of a difference here, and again, I'll get into more detail in a little bit. Now, looking at glucose over there, D-glucose is our naturally occurring glucose, and it's the one that fuels our body, our cells, and all that good stuff. And what I want you guys to look at is the OH that's on the bottommost chiral carbon, and at the cross points right there, and there, those 4 cross points right there, you have carbons, and those are your chiral carbons. The achiral carbon on the bottom here is drawn as a regular C, and then at the top, that's not a chiral carbon, but you don't see it, and I'm sorry it's that way. It's just kind of convention. We'll do some more practice later. But I want you to notice how the OH on this bottommost chiral carbon here points to the right, and how the OH on that one points to the left. Okay, so the L kind of goes with the OH pointing to the left down there. Again, what on earth am I talking about? Don't worry, we'll do some more digging on this one. Okay, so thought this was kind of funny. Got some Samuel Jackson enantiomers here. So there you go. Samuel L and Samuel D Jackson.
I think dimensional actually.
What's that?
That would be more of a dimension. That would be a scientific way, which is, you know, virtual parallel universes.
Maybe you can make a chemistry movie and you have Samuel D Jackson and Samuel L Jackson.
Well, what you're saying in reflection is he could be good in one side and the other side could be. That's a parallel.
That sounds like a Marvel movie. Yeah. Okay. That's kind of awesome. Okay. So enantiomers, they're super duper similar. So how do we tell the difference between them besides ingesting them and seeing what effects they have? And again, I'm sorry about some of the formatting issues when I go from PowerPoint to PDF. Sometimes it just like wow all over the place. So the melting point and boiling point right here, there should be a degree symbol up there. So enantiomers are exactly the same in their melting point, boiling point, refractive index. So this thing right here, that should be an N with a capital D as a subscript, and that's the refractive index. Do not worry about that for this class. It's just one of the properties of a compound, okay? So like a melting point or a boiling point. The density and the heat of formation. Density is something you should know. Heat of formation, if you took Gen Chem, you'd go over that. You went over it a little bit in 2A, but I don't think you would probably remember it too much. But anyways, the point of this is that our enantiomers have exactly the same properties, so how on earth do we tell them apart? Well, we can tell them apart with how they rotate plane polarized light. And I want to point out first, before we go on to that slide, that if we have a couple of enantiomers of lactic acid, so this is lactic acid right here, and if we draw it in 3D, we can have R lactic acid, or its mirror image, which is its enantiomer, S lactic acid, because we have a chiral carbon there. So can anyone tell me which of the carbons, left, middle, or right, is the chiral carbon and lactic acid? Is it this carbon right here? No, because it's bonded to what? 3 hydrogens, 3 of the same thing, right? And the definition for our chiral carbon that we were using is that it's bonded to 4 different groups. What about this one right here? Yes, so it's very easy to see that H and OH are different groups, right folks? Okay, and then the common student mistake is to go, okay, it's connected to 2 C's, that's the same thing, it's not chiral, but we can't stop there, we have to look at this whole group. So this group over here, the CH3, is it different from the COOH right there? Yes, no, maybe so. Yeah, it is. So let me circle those in with color so you guys can see them. So we've got our chiral carbon right there, which is what we're drawing right there and right there. Okay, so we've got the methyl group, and the hydrogen, the OH, and the COOH. So now is it clear that there's 4 different groups bonded to that chiral carbon that we identified with the asterisk, folks? Yes, no, maybe so? Okay, and then if we arrange them in 3D, we can have R lactic acid, and if we pop these off and switch positions, then we'll get the mirror image, the S lactic acid right there. Those 2 things, R lactic acid and S lactic acid, they have the same melting point and the same boiling point, so 53 degrees Celsius for melting point and 122 degrees Celsius for boiling point. Same refractive index, density, heats of formation, all of that stuff. So how are we telling the difference? Well, we're gonna stick it in a glass tube. So whatever our enantiomers are, if we wanna tell the difference between them or see if we have a mixture of them, we're gonna stick them into a glass tube and have them be in a solution. And we're going to shine a plain polarized light at it. And this happens in something called a polarimeter. So there's an old school manual style one, and here's a newer one, and you've got your little tube right there. So you would dissolve some of your stuff, if it's a solid, into a solvent in there, and then we take a reading on it. And let me go back to the previous slide to show you what's going on inside this thing right here, which is called a polarimeter. Okay, so inside the machine is this little tube, okay? So inside the polarimeter. And if you have a sample of something that's optically inactive, it's not gonna rotate the plane of the plane polarized light. So that would be something where you don't have an enantiomer. And what on earth am I talking about here? We've got a sample, it's dissolved in here, and we're gonna shine some light. And light waves go all over the place. But we shine it through this little disc right here that has a slit on it, and then only the wavelength that is like that goes through the slit, like that, can come through. So now it's on a plane, so it's plane polarized. Are we okay with that, folks? Yes, no, maybe so? Okay, so anything that's like going like this or like this, it gets squished out, and you only have this plane polarized light right here. Then that's gonna hit the sample, okay? If you have an enantiomer in there, it will rotate the plane polarized light. If you have something in there that's optically inactive, it's not going to rotate plane polarized light, okay? So something that doesn't have an enantiomer, the light will go straight through, and it'll hit the analyzer right there, and this is supposed to picture that it's perpendicular, but it's kind of hard to draw something in 3D on a 2D surface. So this is hitting it straight on like that, and you get an angle of rotation of the light of 0 degrees, and what you observe is something called a dark field. Now, if you have a sample that has an enantiomer in there, what you might find is that the plane polarized light comes through and it hits it, and it's gonna rotate the light a certain angle, and so it hits the analyzer, and we're gonna detect the angle that it's rotated at. Now, two different enantiomers, like the R and S lactic acid, one will rotate the plane polarized light in one direction, and the other will rotate it in exactly the same amount or same degrees in the other direction. So if one rotates the plane polarized light, say like positive 15 degrees, the enantiomer will rotate it how much? Negative 15 degrees. Does that make sense? Okay. So that's the difference between two enantiomers. Now, different compounds, their enantiomers will rotate plane polarized light a different amount. Okie dokie smokies. Okay? But if you have the same compound and you have the two enantiomers, it'll be exactly opposite. So again, same melting points, boiling points, densities, blah, 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 but they rotate the plane polarized light in opposite directions, but the same amount. So, if you have a sample that's optically active and it rotates plane polarized light to the right or clockwise, that's called Dexter Rotatory. And that's symbolized with a plus sign. If your sample rotates plane polarized light to the left or counterclockwise, that's called level rotatory. And you get the minus sign on that. If one of your enantiomers is positive, the other one will be what? Negative. If one of them is negative, the other one will be what? Positive, yeah. If one is R, the other one is S. If one is positive, the other one is negative. If one of them is D, the other one is L. Are you guys okay with how to match up our enantiomers there? Kind of, sort of, maybe? Okay. The weird thing about this is that your R and your S don't match up with plus and minus. Because I know in our brains we're gonna want to have things that are R be plus and things that are S be minus, but it doesn't always match up that way. So, anyways, we've got our positive and our negative lactic acids down there. This one right here, if you put it in your sample tube and put it in the polarimeter, it's gonna rotate plane polarized light which way? To the right, or clockwise, okay? And that one will to the left, or counterclockwise. One is Dexter Rotatory, the other one is level rotatory. Are we okay with that, folks? But those two will rotate plane polarized light the same angle, just in different directions. So, are we okay with this, folks? Kind of, sort of, maybe? Okay. This is what I was saying about the R and the S thing. So, you will have chiral carbons if you've got enantiomers there, and I've identified them. One of them is S and one of them is R. The S lactic acid right here is Dexter Rotatory, which is not what we want. Like usually in our brains we're like, I wanted to put the S with the minus, but it doesn't always work that way. You can see there that the R lactic acid is level rotatory. Whereas with your glyceraldehyde, the R enantiomer rotates plane polarized light to the right, and the S enantiomer rotates plane polarized light to the left. So here, the R is Dexter Rotatory, and the S glyceraldehyde is level rotatory. So, one of those things we're talking about the orientation and the priority of the groups around our chiral carbon, and the other thing we're talking about is, does the specific enantiomer rotate plane polarized light right or left, okay? So I know we want those to correspond, but they don't. But what I want you guys to get from this is if one enantiomer is S, the other one's what? R. And if one of them is positive, the other one is what? if one of them is negative 20, the other one will rotate the light, what? Positive 20 degrees. Good. Okay, are we okay with this? Comfortable with this so far? Kind of, sort of, maybe? This chapter's a little bit different from the other ones, huh? Yeah. Okay, so this slide right here has a whole lot of those formatting weird things. So let me correct and put some alphas in here. So this right here should be the alpha symbol in parentheses. Same with this one. No sighing back there. And this one too is the alpha symbol. Okay, so, oh, one more. The A should be the alpha. Okay, folks, so optical rotation, we're talking about rotating plane polarized light here. And compounds that rotate the plane polarized light are called optically active. I know I've said that a few times, but this stuff is kind of weird, so I'm saying it again. So the angle right there that we rotate, that we have our enantiomers rotate the plane polarized light, is not what we're gonna report when we write out our report and maybe publish it and it goes into the literature. What we're gonna wanna do is take the angle and divide it by the concentration. So you guys have got that right there of your solution and your path length. So that is the C and the L that appears there, okay? So when you have the alpha symbol in the brackets, what it's telling you is we took the angle of rotation and we divided it by the concentration in that little glass tube and the path length of the glass tube. Now the thing is, why we do this is because if you have a sample in that tube that is more concentrated than, say, the lab down the road, what's gonna happen is that when that plane polarized light hits those enantiomers and it's really concentrated, it will rotate the plane polarized light more because it's hitting more of those molecules. So what you have to do is you have to divide by the concentration to correct for the fact that your concentration was higher than the lab down the road. So if you get an angle of rotation of 3 and your concentration was 3, but the lab down the road had an angle of rotation of 1 and their concentration was 1. Do you guys see how dividing by the concentration makes the results the same? Okay, good. The other thing is the path length. Most of the path lengths are pretty standard with our tubes of 1 decimeter, which is 10 centimeters, so that DM is decimeter. But if you have something different, you have to divide by that path length because same thing as with the concentration. If you have a longer path length, then your plane polarized light has a longer track to hit those molecules. And if you have a short little track like this and it hits those molecules, it'll rotate a certain amount. But if you have a whole lot more, it has more chance of hitting the molecules and it'll rotate more. Does that make sense, folks? We have to divide that out. You guys are kind of quiet today. Okay, all right. So, I think I need to do another little correction here. This right here is the alpha symbol. Okay, so what we'll often see is that our specific rotation, so here has some other little funny things on them, and this here and here, that's a temperature, folks, okay? So if you want somebody to be able to reproduce your research, you want to give them all the conditions that you use so they can get the same results and verify the experiment that you did, because it's really nice if someone else is like, hey, what you're reporting is true, I got that too, because then you're like, yes, I did it correctly, right? I got a couple of yeses, yay! And then that D right there, that's called the sodium D line. So we take sodium metal and we vaporize it, And it's light made from the vaporized light, and that's usually a wavelength of 589 nanometers. So we're just saying which light we're using, so we can be consistent with the results there, folks. So don't be scared about the 20 and the 25 and the D and all that. That's just giving you some more information. Okay, so specific rotations, here's some of them down here. Do not memorize those, folks. What you should know is that the enantiomer will have, let's say, this one right here. So we have L-lactic acid. It says that you've got a specific rotation of -4. So the enantiomer of that one will have a specific rotation of what? Yeah, the positive version of that. Are we all right with that, folks? Yes, no, maybe so? Okay. So I should probably get a little chart that shows how one is the minus and the other is the positive, but this one showed a lot of things that we would recognize, and it's showing you the active enantiomer on those ones. Okie dokie smokies? Kind of, sort of, maybe? Okay, lots of sighs and yawns and all that good stuff. Okay, so as an example of this, here you folks go. We've got R and S glyceraldehyde, and this should be a little 20 up there, but again, weird formatting. And what we have is a positive 13.5 for our specific rotation, and for the S-glyceraldehyde, we have exactly the opposite over there. Now these things right here, the milliliters and gram to the -1 and decimeter to the -1, those are just your units. Don't freak out about that. So this right here, what we would have is milliliters over grams times decimeter. Have you guys seen the, like when something's to a -1 power, it means that it's in the denominator? Are we kind of sort of familiar with that? Okay, so there's a little bit of formatting weirdness there, but what that says is gram to the -1 times decimeter to the -1. Are we okay with the dot also? Yes, no, maybe so? Okay, I just have to ask, because now I get all the new Common Core math stuff, and in 2A I was doing some math, and I had to like carry the one. People are like, we don't do it that way anymore. I'm like, you guys don't carry the one and borrow anymore? Like, you do? Okay, one person says you guys do. You guys are like, I just use a calculator, ma'am. Right? Okay, so anyway, so when it's something to the -1, we write it like this because it doesn't take as much space like in a textbook. But what the -1 means is actually in the denominator. So see how this doesn't have anything up there? So if it doesn't have anything, you assume that there's a what there? +1. Yeah. So every number, every unit, if you don't see a little exponent on it, it just means it's a +1. Are we okay with that, folks? Okay. Questions for me? Concerns? Complaints? Kind of sort of okay on this stuff? Okay, alright. What happens if we have a mixture of our two enantiomers? Well, the mixtures are called Racemic Mixtures or racemates if you have 50% and 50% of each of them. And if you mix them together, what is really weird is that you get different properties. So if we have lactic acid, whether you have R or the S version of lactic acid, you have a melting point of 53 degrees Celsius. But if you mix these together, you get something called a melting point depression. So if you have the R and the S, which are like, oh my goodness, almost the same molecule with all the same properties, and you mix them together, we would expect that two things with melting points of 53 degrees Celsius would have a melting point of 53 degrees Celsius when they're in a mixture, right, folks? But this is chemistry. Ah! Right? This is like this weird concept. When you mix these things, all of a sudden the melting point goes down. Weird, but it does that, okay? Now, if you want to indicate a racemic mixture, what you would do is you'd put the plus and minus symbol in the front. So if you just have the plus, you have the Dexter Rotatory version, and if you just have the minus, you have the level rotatory version, and if you have a mixture, you'd put the plus and minus together. Now this part of it should make sense, folks. If you have 50% of your plus lactic acid and 50% of your minus lactic acid, you put them in a mixture, and one of them is rotating the plane of polarized light in one direction and the other exactly the same angle in the other direction. Does it make sense that then your rotation is going to be 0? If half of your molecules are trying to rotate one way and half of the other ones are trying to rotate exactly the same angle the other way, that one should make sense. Yes, no, maybe so? Okay. So that's what happens when we have a Racemic or a Racemic mixture. Okie dokie smokies. And still this is like when we put it in that little tube in the polarimeter. Questions on this from me?
We're gonna do no calculations.
No. 2B, no calculations in 2B. I just showed you this right here to show you where the units and stuff come from. So what I would expect you guys to know is that if our glyceraldehyde has a specific rotation of plus 13.5, S will have what? There you go. And the machine that you did this to find this out in is called the what? The polarimeter. There you go. Does that make sense, folks? No calculations. If you want to do calculations, you take different chemistry classes, but this is the no calculation class. Yay! And as always, I need to talk to you guys about drugs, because that's the fun part about this class, right? Drugs. Okay, so Celexa and Lexapro. So Celexa and Lexapro, these are drugs that we use for depression and anxiety. And we have a couple of enantiomers there. So we have the R citalopram and the S citalopram. And in this case, the R is lever rotatory and the S is Dexter Rotatory. And I know we want it to be the other way, but remember the R and the S do not correspond with the plus and the minus. Okay, so what's the story on this stuff? Well, Celexa, which was the first one that was produced, is a Racemic mixture of both the R and the S. And drug companies in this country make a whole lot of money. So they produce something and they patent it and they hope that everybody uses it. So they send out their little drug reps to the doctors and give out free samples and all of that good stuff. But eventually their patent runs out, which is called the patent cliff, and they're like, no! And the other drug companies are waiting to make the generic version. And so is all of Canada, because they're like, yay, that's what we do, we give out cheap generic drugs. What's that?
Mexico too does that.
Yes. I have Canadian family members who go for surgery and drugs in different countries because it's cheaper. Yeah, okay, where was I? Oh, Celexa and Lexapro, yes. Okay, so what happened was the drug company that made Celexa was like, oh no, like this is gonna go over the patent cliff, so we have to do something. And they had done a lot of research on this because, obviously, and I was just looking for the name, Lundbeck and Forest Laboratories. So what they did was like, they said we have to keep making money. So they made a version of this drug that was just the S enantiomer. So it's something that's called Enantiopure. So you don't have both enantiomers in there. So making the mixture is cheaper, and making the Enantiopure version of it is more expensive and tedious, and you have to do some more research on how you're gonna develop that, okay? And because it is the Enantiopure S version, they called it S citalopram. Super exciting, huh, you guys? The S version. And they called that one Lexapro. And they got a patent on that one in 2002. And then along came a drug company named Teva, and they tried to make the generic version of it. And Lundbeck and Forest Laboratories took them to court, and they said, no, we have a patent on this. And Teva was saying, you can't have a patent again on this because you've already had a patent on this. And Lundbeck and Forest Laboratories are like, no, we had a patent on the mixture. Now we have a new patent on the Enantiopure stuff. And Teva's like, that doesn't make sense because, like, anyways, the court sided with Lundbeck and Forest Laboratories and gave them an extension. So they got to have their patent upheld for Lexapro. So anyways, that was the whole story on something called evergreening, drug evergreening. So to try to use your previous research to make some more money by having an Enantiopure version. So like we talked about with some of the other drugs, oftentimes one of the enantiomers is the active ingredient and the other enantiomer is inactive. Sometimes it's toxic. We try not to put those ones out on the market, but in a lot of cases it's just an inactive ingredient. Does this make sense, folks? Yes. Makes perfect sense. Okay. So yeah, this topic this was like, I think this was when I was in graduate school. This was like a huge controversy about evergreening and should we be able to do that and making money off of people with drugs and the whole big pharma thing and all that. Yes, sir.
There was one company founder, Chiral, he actually did founded a pharmaceutical corporation that made a patent that was for those who have diabetic problems.
Is that the guy that like increased the price of insulin or something?
Yeah, he's still behind bars for something B2B.
Well, I'm not too upset about that. But okay. Oh, before I go on, folks, does anyone have any questions on this one, on enantiomers and drug design and whatnot? Okay, all right. So, if you got a bottle of one of those at home, Celexa or Lexapro, take a look to see if you've got the name citalopram or S citalopram on there. Now I'm going to move on to something different called Fischer Projections. So Fischer Projections are a different way to draw our molecules, and we hit on this slightly before when I was showing you guys glucose, the two enantiomers of glucose, D and L. But Fischer Projections are a way that we can represent a 3D molecule in 2D. And let me grab this guy right here. Okay, so blue's in front, green's in back. Okay, the other one. Okay, so the W right here is the yellow one, the other ones correspond. Okay, so this is a way that we're going to represent a molecule with the chiral carbon or more than one chiral carbon in a 2D surface. So what we do is we squish it flat, like that, okay? And then it becomes that, and then it becomes this right here. Do you guys see how that corresponds? Kind of, sort of, maybe? Okay, now the thing about your Fischer projection is the bonds right here that are horizontal, we have to know that they come out at us, and the bonds that are vertical are going back into the page. And wherever you have a cross point like that and a carbon is not drawn, that's indicating there's a chiral carbon there, okay? So it's a really quick way for you to look at a molecule and see how many chiral carbons are there. And that's important when you have a really long chain. So again, this is drawn flat, but the horizontal things are coming out at you and the vertical things are going back into the page. So if I drew those with dashes and wedges, what that would look like is this. These things will be coming out at you, and the vertical things are going back like that. Okie dokie smokies. Questions for me? Concerns? Complaints? Okay, moving right along. So this slide just says exactly what I said before. So let's see if we can line this thing up. Okay, so there we go. We've got our chiral carbon in the middle, and we often draw it like that so you can focus on which one is the chiral carbon. And if we squish it, let's see, they rotated it a little bit like that. Okay, so if we squish it, you guys see how these ones come out and these ones back here are going back into the page? Okay, so again, I just rotated it a little bit like that and squished it. And then took the C out and just made it at the cross point so you can go, oh, that's got one chiral carbon. See how the green carbon is drawn and the blue carbon is drawn? That's supposed to indicate to you like right away that those carbons are not chiral. Now the blue carbon at the bottom, do you see how it's bonded to two hydrogens? So is that evident to you? Like, is that obvious to you that that one's not chiral? Kind of, sort of, maybe? Okay. Now, the one at the top, the CHO, this right here, that's just shorthand for C double bond O and an H. So you have an aldehyde functional group up at the top. You guys kind of sort of remember aldehyde? Anyways, the CHO, that's shorthand for that. Sorry about that, folks, but it's chemistry. And we love to do that to you guys, right? No answer. Okay, so the green one written at the top, if I write it out like that, can you see why that is not chiral? Okay, so that carbon has a double bond to the oxygen. So how we think about it is that it's bonded to that oxygen twice. The same thing. Okie dokie smokies? Okay, so again, Fischer Projections, it allows you to see right away where your chiral carbons or your chirality or your stereocenter is. Okay, folks? Horizontal, those things come out at you. Vertical, those things go back. You guys look really tired. You have like midterms and papers and stuff this week? Some of you are like, no, I'm free. Others are like, yes, they're all in the same week. Right?
No, I was stuck in the chiller all day.
You were what?
I was in the chiller all day.
You were in the chiller all day, so you're kind of cold? Yeah. You're very chill, sir.
No, not fun.
It's not fun, I'm sorry. Do you work at Costco?
No, Amazon.
Oh, Amazon, okay. Way back when I worked at Costco, and the freezer days are awful. I don't want to do that ever again. Okay, so a little bit more complex here, folks. So taking a look at some other molecules. Just from what we just learned, this molecule right here, you don't even need to know what it is. How many chiral carbons does it have? Two. What about this one? Four. You guys see that? How Fischer Projections are just like, bam, they show you where your chiral carbons are. Good, bad, ugly. We're good. Okay, I'll keep going. So, if we have a big old molecule, like this one right here, and I made it for you guys so you can see it. So this one is this one right here. And molecules are not flat and two-dimensional like this, but we draw it like this so we can see what's going on a little bit better. So if we have this right here, this is this carbon up here that's double bonded to an oxygen and a hydrogen. So you can do this because single bonds have free rotation. Now, at that point right there, these things are supposed to come out at you. So do you see how there's a hydrogen here and an OH here? Are we okay with that, folks? And then these two bonds are supposed to go back. So that's what that looks like. Now, if we move on to the next chiral carbon, what I'm going to do is rotate it like this so that the OH, and I just put a red ball right there. You guys just imagine that there's a hydrogen coming off of it, okay? So those are coming out at you like this, and then these two bonds right here are going back. And then if I do it for this one right here, the hydrogen and the OH are coming out at you, and this bond are going back. Are we okay so far? Yes, that makes sense.
Yes.
Now, there's another one right here, so we'll rotate it again. So you've got the hydrogen and the OH coming out at you, like that. And then that bond and that bond are going back. And then at the very bottom, we have the carbon drawn in. So is it chiral or achiral? It's achiral. It's not chiral. And you can see that it's bonded to the same thing right there, those hydrogens. So is that obvious for us? Okay. And that is this guy on the end. A couple of hydrogens and the OH. Now what they're drawing over here is how we just looked at it, like where we curled it around, and they're like, you have to think about curling it around a barrel, like that. That was the whole point of that thing right there. Okay, folks? Kind of, sort of, maybe? Okay, good. Questions for me on this? Fischer projections allow you to see what? Chiral carbons. Boom! You get to see them right away, okay? Alrighty. Okay, if you take a chiral carbon and you pull two of its branches off and you interchange them, we've seen this before, you're going to get the other enantiomer. And the enantiomer is going to be the mirror image. So do you guys see all of this stuff kind of coming back at us? We all right with this? Okay, so with Fischer projections, it makes it pretty easy to see if something is a mirror image. Now you see the CH double bond O up there that I circled in blue. That bugs students sometimes because they're like, that's not the mirror image. If I had a mirror image, then it would be drawn exactly as the mirror, and it would look like that instead of like that. But the weird thing about Fischer projections and chemists is at the chiral carbon, we often draw the mirror image, and then we're not concerned with the achiral carbons, and so we just draw them the same direction because we like to torment our students. Just kidding, I don't know, we just do it that way. So if you need to draw this backwards so it is like definitely the mirror image, go ahead and do that. And you can put like the H2, this right here on this side, and the OH over there if you need this one to be that way also. But can you see at the chiral carbon how we have the mirror image drawn, folks? You guys okay with that? Okay. So, yeah. So it makes it easy for us to see how many chiral carbons there are, and if two molecules are enantiomers or not enantiomers. All right, folks. Questions for me? Okay, moving on. Oh, I already did this one for us. Hold on, let me get rid of all the answers. There we go. Okay, so we're gonna draw the enantiomer for the molecule on the right and draw its molecular representation with dashes and wedges. Which one is R and which one is S? We'll get there in a second. Okay, folks, so what we would do is we just go ahead and draw the cross. And if you need the little dash in the middle to like indicate to your brain that there's a mirror there, go ahead and draw that. That's fine. If you don't need it, that's okay too. You guys see what I mean?
Yes.
Okay. Now, on your horizontal line, where you have the chiral carbon, make sure you draw those mirror image style. Are we okay with this, folks? We interchange those two. Now the one on the top and the one on the bottom where the carbon is drawn in, those are your achiral carbons. So you can draw those same left to right, or you can draw them like definitely mirror image if you want. So you could do it like that, or if you wanted to, because you're like, I must have the mirror image, or closer to the mirror image, you could also do that. Okie dokie, Smokies? Alright. So these two are enantiomers. Will they have different melting points? No, they'll have the same melting points. Will they have the same boiling points? These two? Same densities? What's the difference gonna be? Yes, the angle of rotation. When you throw it in that glass tube in the polarimeter, one will rotate the light to the right and one will rotate it to the left. Same angle, but opposite directions. Are we okay with that? Okay, so it says draw a molecular representation with dashes and wedges, and so what we might do for that one is just go ahead and go okay. And the vertical ones have dashes. Are you folks okay with that? Okay, now translating this right here with these dashes and wedges into a style that we're used to with regular, a couple of regular lines. Like that, where you have something like this that you're drawing. Most of the time that will really be helped out with a model, okay? Like going from one of those to one of those over there. Like the model helps a lot. A lot of times with the bigger molecules, I often have to use the models too. So don't worry too much about going from this one in the circle here to something like that. If I were to ask you to do that, I would give you a model kit to do that, so you could rotate them around and see if they were the same. But I would expect you to know that the horizontal bonds are coming out at you, so if you were to draw them with dashes and wedges, the horizontals would be dashes, and the vertical bonds, the horizontal bonds would be wedges, and the vertical ones would be dashes. There, I got it right. Okay, are we okay with this? Kind of, sort of, maybe? What's that?
Which is the answer, basically? Was it the one that the mirror version or the new version that you just drew?
So the question asks us to draw the enantiomer. So the mirror image there is the enantiomer. So this is one enantiomer, and this is the other one, because we exchanged two of them. You see the mirror image here? So organic chemists will draw the mirror image at the chiral carbon, and then wherever you have the achiral carbons, they just leave it in left to right version because we're not really interested in that. Does that make sense? Okay. And then the next part of the question says, go ahead and draw your representation with dashes and wedges. So we put the horizontal bonds with wedges, and we put the vertical bonds with dashes, because these ones are supposed to come out at you, and that's what the wedge means. And those two right there go back into the board, which is what the dashes mean. Does that make sense? We okay there? Okay. Now, if I was teaching organic chemistry folks, I would expect them to look at the 4 different groups and prioritize them and figure out, is it right-handed or is it left-handed, which one is R and which one is S. For this class, I would say one of them is R and expect you to know that the other one is what? There you go. So, was there a question in the back, folks? I heard but didn't quite pick it up.
Oh, is it
Yep.
R is on the right?
R is on the right. So we have R here and S here. Is that what you were saying? Hold on. Not quite sure that I heard you. What was that? R is on the right and S is on the left. Is that what you told me? And did we get that from this page right here?
No, I just, because CO2H is the first and then the second is the NH2.
Oh, you mean the priorities? You
Yeah.
went ahead and prioritized them? Yay! I have an organic chemist here.
No,
You've seen this before?
no, it's just because it wasn't a lecture, right?
Oh, okay. You definitely don't need to know that for this class. You know that? Or
Or,
were you just looking at the slides?
yeah.
Okay. Yeah, in the lecture I told you guys, like, that was just like, how do we get R and S? And I was showing everyone the background.
Yeah,
And,
this is looking at.
okay, good. All right. Where was I? Okay, number two. Oh, and by the way, my friend right here was correct. We have an S here and we have an R here. So, yay, you. Again, folks, I wouldn't expect you to be able to pick out which one is R and which one is S. I would give you one, and you gotta pick the other one. Okay, tell me. Now, number two says, how many chiral isomers does D-glucose have, folks? Or D-glucose here? 4. 1, 2, 3, 4. So are we seeing how the Fischer projections allow us to see the chiral carbons right away? Okay. Now, just another thing to mention again, folks, sometimes you'll see this right here drawn as the little elbow, and you don't see the carbon drawn in there. You just kind of got to know that if it's C double bond O, it's not chiral, it's a chiral, okay? All right, so we've got 4 chiral centers there, or 4 chiral carbons. And they're all at the cross points. Now, it says for us to go ahead and draw L-glucose. So for L-glucose, what you guys are gonna wanna do is draw 4 lines where you have lines on the previous molecule. And then go ahead and put a vertical line in there. And draw exactly the opposite orientation of your branches at each of the chiral carbons. So that's gonna be the mirror image there. So right here, on this guy, on the left, we would put what here? OH. So on this one right here, you have OH here and you have H here. What about this one? H, and then what's on this side? OH. So you have the opposite orientation in each of your chiral carbons. Okay, now at the top and the bottom you can draw them mirror image style, or you can draw them left to right style. Those ones don't matter because we're not interested in those. So I usually just write them left to right. On the top one, instead of drawing it out, you could also write CHO, which we saw in another molecule on another slide. Okay, folks? Yes, no, maybe so? Okay. So if the molecule on the left is called D-glucose and the molecule on the right, the enantiomer, is called what, folks? L-glucose. There you go. So here's another isomer flow chart. We've seen this before. Slightly different version, but I just wanted to show you again to kind of show you where we're at. So we've got our constitutional isomers and our stereoisomers. And our constitutional or structural isomers were the ones where we had, say, like 1 fluoropropane versus 2 fluoropropane. Same molecular formula, just different connection of atoms. Are you guys okay with that side of it? Okay. And then over here we had stereoisomers. And the 2 types that we had that we talked about before were cis-trans isomers, and we said that there were a couple of others like rotamers that we weren't going to talk about, conformers and rotamers, unless you took Chem 12A and 12B. And then we also have enantiomers. So cis isomers and enantiomers. So this is the area that we're in right here. You guys all right with that? Just to show you where we're at? Okay, good. All right, so what happens when we have more than one stereo center or more than one chiral carbon? Come on. It's not participating. There we go. Somebody is getting a call. All right, so the molecule up there, 2,3-pentane diol. Now, the all at the end is telling us that we have what kind of molecule? We have an alcohol. Not only do we have an alcohol, but we have a diol. So we have an OH at two different spots, or we have two OHs. They could be on the same carbon, but in this compound, they're not. So the pentane portion of it indicates that we have a hydrocarbon chain that has how many carbons in it, folks? 5. So pentane is telling us we have a 5-carbon chain. The diol on the end is saying you have 2 OHs, the 2 and the 3 up front. They're telling you that one of the OHs is on carbon 2 and the other OH is on carbon 3. Are we okay with that? Okay, so if we were looking at 2,3-pentane diol, we might go, okay, that's not too bad. That's a pretty standard molecule there. But the thing about that is that 2,3-pentane diol has how many chiral centers? It has 2. The carbon on the left, number 1, is that chiral? No, carbon number 1 is not chiral. It's achiral. Why? It's bonded to 3 hydrogens. It's bonded to more than one of the same thing. Carbon number 2. Is carbon number 2 chiral? Yes, it's bonded to 4 different things. It's bonded to hydrogen OH, the CH3s, it's carbon number 1. I see you in the back there. And the big blob on the right-hand side. So right here, we've got a chiral carbon. What about the carbon next to it? Yes, it's bonded to 4 different things. Carbon number 3 is bonded to OH and H. Are we okay with the fact that those 2 things are different? Then whatever it's bonded to on the left is different than the ethyl group, the CH2, CH3 on the right. You guys all right with that? Okay, so that one is also chiral. What about carbon number 4? Is that chiral? No, because it's bonded to 2 what? 2 hydrogens. Those are 2 of the same thing, so that's not chiral. What about carbon number 5? Nope, because it's bonded to 3 what? Hydrogens. Is bonded to more than one of the same things. It is not chiral. Okay, we've got 2 chiral carbons, folks. The first chiral carbon can be either R or S. And the second chiral carbon can be either R or S, because molecules are not flat like that. They are 3D. And in the picture below, we can see this represented. Now, I wish that this picture would do carbon 2 here and carbon 3 there, because that's usually how our brains orient it, but it's got it the other way, so I made us some models. Yay! Okay, so give me a second here. Oh, I brought my R and my S today, so I've got these 2 guys right here as opposed to those 2 guys. Okay, so let's see. We've got S and R. Oh, I should have done a green one, but I did 2. Okay, let's do S and R. Okay, so this should be green right there. I'm gonna make it correspond for you folks. Get over there. got that guy right there. And I have to borrow a green one. Are you guys laughing back there?
No.
I hear you.
It's like you drink too much coffee.
I drink too much coffee. I'm too happy today.
No.
Oh, you drink too much coffee.
No, I don't know why, but like for some reason coffee gives you a bunch of anxiety. I don't know. So like I'm listening to you and I don't understand and I just drink coffee, so I was just like
Well, okay. Good thing we have like models to the rescue here. So, okay, two, we got R in the front and S in the back. Hold on, just let me get these corresponding for you guys so you can see. You got the jitters back there, huh? Okay, so we got R and S. Okay, do those look the same, folks? It's easier for you to see it back there than it is for me, like right here. Looks like those are matching up.
That looks kind of the same.
Yes, no, maybe so. Okay, if we've got one of the balls that's not the same color or some other orientation, scream out at me, but I think we got it right. Okay, so the point of this is at each of those chiral carbons, carbon 2 and carbon 3, we can have either an R or an S orientation. Now, if you have an enantiomer, your carbon at R that's an R in the enantiomer, it will be what? S. I wasn't trying to trick you folks, okay? If you have a carbon that's R, the enantiomer, that same carbon will be S. If you have a carbon that has the orientation of S in the enantiomer, it'll be what? It'll be R, okay? So 2,3-pentane diol has these 4 different versions here because both of your chiral carbons, carbon 2 and 3, can both have an R orientation, or they can both have an S orientation, or you can have carbon 2 is S and carbon 3 is R, or carbon 2 is R and carbon 3 is S. Now, if you have an enantiomer, every single one of your chiral carbons needs to be opposite of the original enantiomer. So if we look at the 2 on the bottom that we made the models for, folks, you can see that on the one on the left, the second carbon has the S orientation. And the second carbon in the enantiomer right there has the R orientation. Whereas with the third carbon in the first molecule right there, we have R, and the second one we have S. So you have exactly opposite. So these ones right here are enantiomers. Are you guys okay with that? Okay. Wherever you have R in one enantiomer, you have what in the other? S. Wherever you have S in one enantiomer, you have what in the other? R. Okay, looking at the ones on the top. The one on the top left, carbon number 2 is S. And if you have an enantiomer, carbon number 2 will be what? R. And it is for that one. So you can see 2R. That means carbon number 2 is the R orientation. In the top left, the third carbon right there has an S orientation. So it says 3S. To be an enantiomer, the third carbon in the enantiomer must have which orientation? R. So these ones right here are enantiomers to each other. So these two are enantiomers and these two are enantiomers, because here wherever you have an S, you have an R. Okay? Wherever you have an R, you have an S. Are we okay with these two are enantiomers, folks? Okay, now these two, even though one of their carbons is R and one of them is S, the enantiomer is opposite. So here, carbon 2 is S, and on the enantiomer, carbon 2 is R. Carbon 3 is R here, and on the enantiomer, carbon 3 is S. Are we okay with the fact that those two are enantiomers? Okay, but all four of these are still 2,3-pentane diol. So how do we relate this one and this one? Or this one and this one? Or this one and this one? Or this one and this one? Well, if we take a look at these two right here, we can see that carbon number 3 is an S orientation here and an R here, so those are opposite, so that counts. But if we back up to carbon number 2, this one is S, but this one is also S, which is not the opposite. So there has to be some other thing other than enantiomers, because these are not mirror images of each other. This is the same, and in a mirror image it would be the backwards orientation, and we call those diastereomers. So this one and this one are diastereomers. They're also called Diastereo Isomers. So what is the relationship between top right and bottom right, folks? Enantiomer or diastereomer for these two right here? That's a weird word to say, huh? That's like all over a mouthful. Diastereomer. Diastereomer or diastereoisomer. So carbon number 3, you've got R here and S here, so those are opposite. But carbon number 2, you've got R here and R here, and those are not opposite. And if you have an enantiomer, every single chiral carbon has to have an opposite orientation. Okay? So these two folks, again, they're what?
Diastereomers.
Good, they're diastereomers. What about diagonal? 2S, 3S versus 2R3S. Enantiomers or diastereomers?
Diastereomers.
Good. Because not every chiral carbon is opposite. What about the green pair? Those are diastereomers also. Is there any question on that, folks? Okay, so if you get a couple of molecules and you're asked, are these enantiomers or diastereomers, you look for exact opposite at wherever your chiral carbons are. Does that make sense? Okay, good. So in case you didn't like my little drawing there it is again. Nice and neat. Questions for me? Yeah. No? Okay, so Fischer Projections, folks. What Fischer Projections are nice for is identifying where the chiral carbons are, and also identifying quickly if something is an enantiomer or not. And if not, is it a diastereomer? So if you take a look at these two Fischer Projections right here, you can see that there's two chiral carbons, and at those chiral carbons you can see the exact opposite orientation, or the exact mirror image. Are you folks okay with that? Okay, so over here, looking at these Fischer Projections, you can see, okay, wow, these have the same molecular formula, same atom connectivity, so we're over into the non-constitutional structural side, we're over there. So are they diastereomers or are they enantiomers? Well, you've got opposite orientation, or the mirror image of that chiral carbon, but you don't have opposite of this one, okay? So because of that, those two are diastereomers. Okie dokie smokies? Alright. So can you see how, like, drawing it in a Fischer projection that other way is allowing us to quickly really see certain things. Okay, so this one right here asked us which ones are enantiomers and which ones are diastereomers. So what we're gonna wanna do is we're gonna wanna look at all of the chiral carbons. So just these two right here as they're drawn. At each of the chiral carbons is their a mirror image, it's their opposite orientation. The first two.
Mirror image.
Those are mirror image. So wherever we have an OH, we have an HO on this side. So they're opposite of each other. So the first two are enantiomers or diastereomers.
Enantiomers.
Yeah, those are enantiomers. Okay, what about 2 and 3? Enantiomers or diastereomers?
Diastereomers.
Yeah, they've got the same molecular formula, they've got the same atom connectivity, but in each of your chiral carbons, you do not have mirror image. Some of them are the same orientation. So this one right here, yep, those are opposite, but this one is the same. And every single one of them has to be opposite for those to be enantiomers. So those two are not mirror images, those are diastereomers. What about 1 and 3?
Diastereomers.
The right here, this top, it's the same. And if you had enantiomers, it would have to be backwards at each of our chiral carbons. And if the first one is not opposite, well, then we're done, right? Does that make sense, folks? Okay, so those ones are diastereomers. Awesome. Okay, folks, it looks like it's 2:10. So, oh my goodness, we finished. Wowee, I thought we had a couple more slides on there, but yay. Okay, so, last night, Nayeli said that, apparently the Zoom office hours weren't working. So in case any of you were trying to come, like Nayeli, boo. I will definitely be there tomorrow morning, 9 to 11. If it's not working, I'm not there for some reason, please email me because I always have my email open in case it's not working so I can like log off and log back in and figure out what's going on. Okie dokie smokies. All right, those of you going to lab, I will see you up there. Those of you not going to lab, I will see you Monday.
Is the quiz good today?
It is. Did you guys need some more time on that?
I finished the last time questions. Maybe I call.
Okay, good.
Thank you.
You ready for Halloween?
No, not yet. How about you?
I stopped going to Halloween a long time ago. I celebrated.
Oh, good.